All right. Hey, everybody. Welcome back. Today, we're going to be talking about something very exciting to me. We're going to be talking about the so-called Christoffel symbols. These are symbols, or rather sort of complicated functions, that we will use to further describe our parametrized surface. And as we do this, let me sort of say out loud where we are going with this. It is ultimately our goal to better understand our surfaces and the most fundamental properties of our surfaces. So far, that's taken the form, of our first fundamental form and our second fundamental form. And each of those have relied on taking our parameterization capital X and then taking the first derivative of X and the second derivative of X in appropriate ways. That's how we computed our first fundamental form and then our second fundamental form. The Christoffel symbols are a continuation of that, and they will really help set the stage for our deepest understanding of surfaces yet. But first, let's not get too ahead of ourselves. I want to sort of talk about where these are coming from, and what my goal is here. So, first of all, let's suppose we have a surface S, and I'm looking at a given point on that surface. All right, let's assume this is a parametrized surface, so I have a parameterization, a capital X of u comma v. Well, we know that as long as the surface is regular, at the point P, the three vectors x of u, x of v, and n will form a basis of three-dimensional space, right? And that just means that these are three vectors in R3. They will all be linearly independent from each other, right? The normal vector will be pointing perpendicular to the surface. X of u and x of v will be pointing tangent to the surface. And because our surface is regular at this point, x of u and x of v are not pointing in the same direction. So in total, these three vectors describe or form a basis of three-dimensional space. What that means is that any vector that is anchored at the point P should be expressible uniquely as a linear combination of these three vectors, right? So any vector v should be uniquely represented as some constant times x of u plus some constant times x of v plus some constant times the normal vector n. And what we want to do today is we want to explore the question of how can we represent this vector v if the vector v I'm interested in is actually my second derivative, right, of the parameterization. So either xuu, xuv, xvu, or xvv. So in other words, the question is this, right? If I can express any vector this way, and if I want to consider my vector, let's say xuu, so that's the second derivative of u, second derivative of x with respect to u, what are the appropriate coefficients that I should get out front of each of these? Now it turns out we've already seen one of these before. The coefficient out front of the vector n is going to be our second fundamental form. In this case, if I'm looking at xuu, that would simply be luu, or in this case, I'm just going to say L11, so that first entry in your second fundamental form matrix. And we'll discuss why that's true in a little bit. But we haven't yet seen our coefficients out front here. And so we don't yet know how to express xuu in this basis. That is what we're going to be talking about today. And that sort of prompts us to introduce the so-called Christoffel symbols. So the Christoffel symbols are going to be functions, which we denote with a capital letter gamma and three different indices, right? Two subscripts and a superscript. So the Christoffel symbols are special functions of the form gamma, upper I, lowercase jk, and these are the functions that satisfy these equations here that we were just mentioning. So if I were to take the u derivative of my parameterization, which I'll be calling the 1 derivative from here on out, I would get some coefficient of x1 plus some coefficient of x2 plus L11 times n. And so these would be my Christoffel symbols. It is worth pointing out That's not quite what I wanted to do. It is worth pointing out that these two right here, right, the 1's down here, are really coming from these 1's out here. So this is saying my second derivative of my first variable, or what we've traditionally called our u variable. So this is my u derivative. I'll just be denoting it as x11. And the 1, the fact that I'm taking the first variable's derivative, or the derivative twice with respect to the first variable, is where these are coming from. The upper index, right, the upper index here is really coming, I'll make that blue, I suppose. That is really coming from this number down here. So that's saying that if I take the second x derivative, the second derivative of x with respect to my variable u, the part of that is pointing in the x1 direction, that is my gamma sub 1, 1, 1. And ditto for this term here. So each of these indices plays an important role. The lower indices tell me which second derivative of x I'm looking at, while the upper index tells me which basis element I'm attached to. Okay, great. And so our goal now is we know that these functions must exist, or we know that we should be able to write each of these vectors uniquely into this kind of a decomposition. The real question now is, how can I express these functions, and can I do it nicely? Because at the moment I have no idea. Now, we might be misled a little bit if we make the observation that these coefficients are actually what we would get if we took the corresponding value and dotted it with the normal vector. In other words, let's take a look at this L21 for a moment. That is the coefficient associated with x21, but that is also the quantity that we get if we take x sub 21 and dotted it with n. Right, and that's sort of pointed out right here. The xjk coefficient of n ended up being xjk dotted with n. That's our L, right? That's our second fundamental form. Is it the case, maybe, it could be the case, that each of these other coefficients, the gamma ijk's, end up being just x sub jk dotted with x sub I? And unfortunately, that is not the case. The reason that L our second fundamental form ended up being the correct coefficient is sort of special. It's because our normal vector is actually perpendicular to both x sub 1 and x sub 2. But it's possible that our x sub 1 and our x sub 2 are themselves not perpendicular to each other. They might be pointing in kind of the same direction, right? They're just not directly on top of each other, that we know. But if they're not orthogonal, then this will not be the case. And so, unfortunately, yeah, we're not getting off that easy. But this expression will be very valuable for us to compute. And so this will turn out being an important thing, and we're going to take a short intermediate step. I was going to say detour, but it's not really a detour. It's an intermediate step on the road to calculating these Christoffel symbols. We are going to calculate what the expression xjk dotted with xi really is. Or rather, I guess I'm going to say we will now calculate xij dotted with xk. And I'm going to have a shorthand for this, right? This is a well-established shorthand. I'm going to use these square brackets, and I'm going to call this ij comma k. So this is just the dot product with my second derivative x sub ij dotted with my first derivative x sub k. And the way that I'm going to do this is I'm going to actually use derivatives of the first fundamental form. So I'm going to set up a system of equations that I can compute, and then I'm going to solve for these expressions here. And so here's how I'm going to do this, right? Let's jump over here. The first fundamental form is this matrix, the Gij's, but each of these is itself a dot product of first derivatives of x. So to pick one at random, the G21 entry is really x sub 2 dotted with x sub 1. What I could do then is I could take a derivative of this expression. So the derivative of g sub 21 with respect to one of my variables. And the end result would be a product rule which would involve terms that look like this. So that's going to be my start. I'm going to start with this, my first fundamental form, and I'm going to take derivatives of the entries. There are 4 entries, although secretly, right? I mean, not even secretly, overtly, this entry and this entry are the same, right? Because the dot product is symmetric. So there's really 3 unique entries in this matrix. I can take 2 derivatives, right? I can either take a derivative with respect to u or a derivative with respect to v, a derivative with respect to the first variable or the second variable. And so as a result, there should be 6 things that I compute. Let's try to compute 1 or 2 of them, and then we'll look at the rest of them. So if we wanted to take the derivative of g11 with respect to the variable x sub 1, that's really taking the partial derivative of x1 dot x1 with respect to the variable x sub 1. This would give us a product rule in which I get the x1 derivative applied to x sub 1 dotted with x sub 1. I realize I'm probably just saying x sub 1 a lot. Let's write it down. So if I apply the derivative of my first variable to this dot product, I'm going to get a product rule, and it'll be the derivative of the first dotted with the second plus the derivative of the second dotted with the first. Right? And then those can sort of merge together. We get 2 times x11 dot x1, and we can write that shorthand as 2 times this bracket right here. All right, similarly, we can compute the g11 derivative with respect to x2. We can do that similarly, and so on for all of the others. And we end up with 6 entries, right? And here are the 6. So we've got each of our derivatives with respect to each of our variables. Notice, as a result, we've ended up with all of these different brackets. And what we can do now that we have this system of equations is we can solve for the entries I, j, comma, k. And when we do this, right, when we isolate and solve for each of those and rewrite them, we can rewrite these brackets in terms of partial derivatives of our first fundamental form. And we do that down here. So we end up getting this equation that the bracket, the sort of intermediate step we were hoping to accomplish, the expression xij dotted with xk is written like this. And this will work no matter what I, j, and k are. Great. I'm going to star this equation for my, my dot product here, because we're going to give that a name a little bit down the road. But for now, I'm just going to leave it like this. So we now have an explicit formula for calculating xij dotted with xk. Perfect. Now, I said earlier that this expression was not the same thing as my Christoffel symbol, my gamma of ijk. And that's true, unfortunately. It turns out, though, that we can use the first fundamental form itself to relate these 2 objects together, right? And here's how, or here's why. Notice, this was my original equation for my Christoffel symbols. I said that my Christoffel symbols were defined as the unique objects that made my xij, my second derivative with respect to I and j, equal this. What I can do now is I can compute the dot product of that with x sub l, let's say, and similarly compute the dot product of each of these with x sub l. So to keep this equality an equality, I can take all of this and dot it with x sub l. Right? And that will equal what I get if I take all of this and dot it with x sub l. And the end result is going to be as follows, right? Over here I'll get the xij dot xl. That is exactly the bracket symbol that we just developed. So this is ij dotted with l. And that will equal, and as we go down the line, notice what we get. The Christoffel symbol will stay the same, so that's going to be 1ij. But x sub 1 dotted with x sub l is going to be g1l. That's G1L right there. Plus, here we're going to get our Christoffel symbol. We'll just stay the same. So that's gamma 2ij. X sub 2 dotted with X sub L is going to be G2L. Plus, here, this will just be 0. Our normal vector dotted with a tangent vector should be 0. And so what we got then is that our bracket is not exactly the same as a Christoffel symbol, but rather it is what we get when we add our Christoffel symbols, or I should say multiply our Christoffel symbols by our first fundamental form and sum them up. And using our brand new summation notation, I can write this in a really nice way. Notice that there's a 1 up here and a 1 down here. Notice there's a 2 up here and a 2 down there. So I can write this as ij comma L equals, and now this will be the sum, right? The implicitly defined sum. We'll have our ij down here. We'll have a k up here times a gkl. And so what I'll get is this relationship between my Christoffel symbols and then these brackets. Okay, and that's exactly what we see up here. All right, so our ij comma L was equal to this expression. And if I use the same trick that I did in the previous video and write my inverse of my first fundamental form, the inverse matrix with superscript, so if G upper IL represents the inverse matrix for the first fundamental form, then I can solve for my Christoffel symbol by multiplying by the inverse matrix to get the inverse matrix over to the other side. And the end result is this equation here. We get that our Christoffel symbol is equal to the G upper IL times the bracket JK comma L. And we sum that as L goes from 1 to 2. That gives us, when I plug in my blue starred equation from the previous slide, that gives me this equation for my Christoffel symbol. And I'm going to denote this with a red star. So this gives us a way to explicitly compute both the brackets and the Christoffel symbols. And I should say, just to make things slightly more confusing, sometimes the brackets are called Christoffel symbols of the first order, while the actual Christoffel symbols are called the Christoffel symbols of the second order, but they're very closely related, as we can see. So these two start equations tell us how we can compute these different quantities just using the first fundamental form. And so these equations are called Gauss's formulas.